In the beginning of 18th century, Joseph Louis Proust stated that hydrogen atom is the building material and all other elements are simply the combination of number of hydrogen atoms. Why? Because the atomic weight of hydrogen is taken as 1. At that time, the atomic weight of all elements were given as whole number. That means they expressed atomic weights in whole numbers only. Let us take a small example here. If the atomic weight of hydrogen is 1, if you want to find the atomic weight of carbon, the atomic weight of carbon is 12 times that of hydrogen. What is the atomic weight? The atomic weight of carbon is 12 times the atomic weight of hydrogen. Hence, if you keep 1 here in place of 1, we will get 12 here. So the atomic weight of carbon is 12. In that way, they used to find the atomic weights by using the atomic weight of hydrogen here. Let us see the important topic right now, that is Dobereiner's Law of Triads. In 1829, a German chemist known as John Wolfgang Dobereiner trying to classify all the elements into groups. So in his classification, he tried to classify the sum of the elements into 5 groups on the basis of their atomic weights. So in each group, it contains 3 elements known as triads. So in his classification, in each triad, the elements are arranged in increasing order of their atomic weight. So in this way, he tried to classify the elements and he gave a relation in each and every group. Let us see what is the relation given by Dobereiner in the next slide. Okay, let us see the Dobereiner's Law of Triads. Here the law states that the atomic weight of middle element is the arithmetic mean of first and third element. Okay, let us take a small example here. I am taking the first group here. In his first group, he kept 3 elements. What are those? Lithium, sodium and potassium. Here, the atomic weight of lithium is 7 and the atomic weight of sodium is 23 and the potassium is 39.0. Okay, let us find the relation between these 3 elements right now. Here, he arranged the elements in increasing order of their atomic weight. And now we are going to find the arithmetic mean of first and third element. It should be equal to the atomic weight of middle element. Okay, here the first element's atomic weight is 7 and the atomic weight of third element is 39. And if you find the arithmetic mean, you will get 7 plus 39, it is 46 by 2. Here we got 23. So here the 23 is equal to the atomic weight of middle element. So in this way, he gave a relation between these elements in a group. Let us see the whole classification given by Dobereiner's Law of Triads. Okay, look at the table, and here the table contains 5 groups. Here up to E, and you also noticed that in each group it contains 3 elements, 1, 2, 3. So in this, he arranged the elements in increasing order of their atomic weight. How he arranged? He arranged the elements into increasing order of their atomic weight. Let us see the first element here in first group. So here the atomic weight of lithium is 7.0 and sodium is 23.0 and potassium is 39.0. In this way, he classified the elements in increasing order of their atomic weights in each group. And also he found that the arithmetic mean of the first and the third element is equal to the atomic weight of that middle element. Okay, in that way he gave a relation in each and every group. But if you see clear here, the arithmetic mean of calcium and barium is not 87.5. Here we got 88.5. So here the rule is failed for the second group. Let us apply the same rule for the remaining groups also. Okay, now I am applying the same method for the third group. So if you calculate the arithmetic mean of this first and the third element, the arithmetic mean is 81.25 only. But here the bromine's atomic weight is 80. So we are not getting that middle element's atomic weight. If you apply the same rule for the remaining elements here like this, it is not valid for the remaining group of elements. But he found that in each group they are having the same kind of chemical properties. In this way, he tried to give the relation, but the rule is failed for the remaining groups. Remember the elements and groups present in Dobereiner's classification. Okay, in the first group he kept lithium, sodium and potassium. In the second group he kept calcium, strontium and barium. In the third group he kept chlorine, bromine, iodine. And in the fourth group sulfur, selenium and tellurium. And in the fifth group he kept manganese, chromium and iron. So we have to remember all these groups. Why? Because they are asking so many questions in your examinations. For that, let me explain one way to remember these elements. So okay, remember the first group as Linak, second group as Kesar Badam, third group as close brother in India, fourth group as Sachin Century Tendulkar, and remember the last group as man crucial feelings. In that way you can remember and each and every group. Now let us see the limitations of Dobereiner's triads. That means what are the defects present in the classification of Dobereiner. So the first defect is all the known elements could not be arranged in the form of triads. That means so many elements are there. We are having many elements there, but he can able to keep very few elements. In his classification. How? Only 15 elements only he can able to keep or arrange into triads. Okay, this is the major defect which was done by Dobereiner. Let us see the second defect in Dobereiner's classification. The law failed for low mass or for high mass elements. That means, so if I want to find the atomic weight of middle element, if the elements having low mass and high mass, it is not possible. So let us take a small example to understand this limitation. Let us take fluorine, chlorine and bromine here. The atomic weight of fluorine is 19 and the atomic weight of bromine is nearly 80. So the arithmetic mean of these two elements are 19 plus 80 by 2 is equal to 99 by 2. That is 49.5. But here the atomic weight of chlorine is not 49.5, it is 35.5 only. See here, there is a large difference between these two values. So for low mass and high mass, it is not possible to take the arithmetic mean of that elements to find the atomic mass of middle element. Let us see the third limitation here. As the technique improved for measuring atomic masses accurately, the law was unable to remain strictly valid. That means if I want to find the accurate atomic weight of any element by using this rule, it is not possible accurately to find the atomic weight of any element. Let us take a small example here. If I take manganese, chromium and iron, the atomic weight of manganese is 55 and here the chromium is 52 and the iron is 56. So if I want to find the atomic weight of chromium exactly, let us take the two elements arithmetic mean here, 55 by 56 by 2 is equal to, okay, see here we got 55.5. The arithmetic mean of manganese and iron is 55.5, but here actually the atomic weight of chromium is 52. Actually if you find the mean of these two, we should get this value, but here we got 55.5. this is a large difference what we got to find the atomic weight of those middle element. Like this, if I want to find the atomic weight of a middle element accurately, this law is not strictly valid.